In this video, we're going to take a look at exponential and logarithmic functions coming from data. So by from data, we mean that we're going to collect some data and use it to generate an equation. So whenever we collect data, we're going to collect it on two variables. One variable we'll call the x variable, the other variable we'll call the y variable. We've done this using linear models earlier, and now what we're going to do is use exponential models. And then later, a little bit later, we'll use logarithmic models too. So let's start out with exponential regression. Basically, just like with our linear models, we can have technology give us and generate out an exponential model. These models are either going to be written as a times some base to the power x, or a times e to the rx. Both of them y equals that expression. So either technology will give you out a model that looks like y equals a number times e to the rx, or a y equals a number times b to the power x. Both of these are actually the same. If b is equal to e to the r power, then these two are identical. Along with our model, technology will also give us out a correlation coefficient. Now, we can call that correlation coefficient R in an exponential model. I want to note that in a linear model, this was a Pearson correlation coefficient. In an exponential model, this is not a Pearson correlation coefficient. And if we're looking at the single R, it's still going to be between -1 and 1, but more likely we'll see our correlation coefficient come to us as an R squared. Sometimes that's capitalized, sometimes that's lowercase. Usually it's capitalized, to be honest. So that R squared will be between 0 and 1. Now, if we're looking at the correlation coefficient just of R between -1 and 1, just like in the linear case, we have a strong relationship if the R is close to -1 or if R is close to 1. And we have a bad relationship if R is close to 0. In the exponential model, if R is close to 1, then it's a strong exponential relationship with exponential growth. If that R is closer to -1, it's still a strong exponential relationship, but now with decay rather than growth. And obviously, if it's close to 0, we do not have a good linear relationship. I misspeak here. It should say exponential relationship. Let me fix that. So close to 0, we do not have a good exponential relationship if we're using an exponential model. Again, most of the time, what we will use in this class is the R squared. That's the more standard notation that comes along with exponential models. And we have to give a place for a cutoff between a good fit model, that is a model that fits our data well, and a model that doesn't fit our data well. In this class, we'll use the cutoff value of 0.5. If R squared is at or above 0.5, we'll say that the model fits the data well. And if R squared is below 0.5, we'll say that the model does not fit our data well. Now, in other classes, they may use a different cutoff value. That 0.5 is what we're going to use in this class because of the size of our data sets and things like that. But other classes may have a different cutoff value, and other circumstances may have a different cutoff value. So let's take a look at an example. So here we have example 1, and you can see the data here on the right. It's a table of the year and the debt of the United States. This is essentially every year from 1981 to 2024. And this data comes from the US Treasury. Now, the actual numbers aren't what we're concerned with in this class. What we're concerned with is how that chart would look. Again, we're looking at the US debt in, this is in billions of dollars, so that's why it says 35,000. That's $35 trillion. Notations there. And we use the debt as the y-axis and the years since 1980. So we're starting at 1981 there with an x of 1 as our x axis. So x is years since 1980. Y is debt in billions of dollars. That's why you can see like 35,000 is technically $35 trillion. And you can see the pattern. This is not a straight line pattern, but it does appear to sort of grow. And then as we go further and further to the right, we're shooting up at a steeper rate. Now, if we use technology, in this case Excel, to give an exponential trend line, you can see we've graphed that exponential curve of best fit right here. And it fits the data pretty well. Some points are a little bit under that line, some points are a little bit above that line, but in general, it fits the data pretty well. And the equation of that exponential equation of best fit is y equals 1,322.7 times e to the 0.0753 times x. And the r squared we get with that is 0.9942. So that's what technology is giving us. It's giving us this exponential equation to fit our data. Now, when I say this exponential equation, realize that y is the debt in billions of dollars. X is years since 1980. Now that I have that via technology, I can answer some questions. I can say, does the model fit the data well? And then find this model's prediction for the debt, that is the debt in the United States, in the year 2025. And then find the model's prediction for debt in 2040. Let's go ahead and do that. So the first thing that we're going to ask is, does the model fit the data well? And in this case, since we have an r squared of 0.9942, that means the model fits the data well. All right, it's above 0.5. That's all we're looking for, r squared above 0.5. So model fits the data well. And then we're ready to do a prediction. So the debt in 2025, remember X is years since 1980. So the debt in 2025 will be a prediction where we set X equal to 45, right? That's 45 years past 1980. So that's what we end up doing. And we'll take this equation, I'll just copy and paste it, and replace X with 45, and then do that calculation in our calculator. In this case, I get Y is equal to 39,180.34 when I round to 2 decimal places. Now, remember, this is debt in billions of dollars. And so that is in billions. If you wanted to put this into trillions, what it would be is 39.18034 trillion dollars, that is. And if you wanted to make that into an actual number, 39 trillion 180 billion and then 340 million. That's the number $39.1834 trillion. So that's what you're looking at as far as the actual number written out. Again, this is rounded, obviously. We can do the same thing for the debt in 2040. That prediction, if this keeps up, now remember, X is years since 1980. Therefore, 2040 is 60 years since 1980. So I just replaced the exponent that was 45, or the piece of the exponent that was 45, with the number 60. And I end up with Y equals 121,228.25 rounded to 2 decimal places. That's again in billions of dollars. And I'll just write the trillion number. That's 121.22825, or roughly $121 trillion. So $121 trillion roughly. So obviously we can do predictions and we can determine fit of models based on what the technology is giving us. Now, in this class, we don't actually have to, I won't ask you to generate out these exponential models, but I will link a couple of videos if anybody wants to see how these exponential models are generated via the TI-84 calculator or via Excel. And I'll have a video for each, the Excel exponential regression and the exponential regression via the TI-84 calculator. This is the one on the screen that was coming from Excel. You'll get the same one either way, but there we go. Here's another example. In fact, there's kind of two examples in here. What this data is about is it is the median marriage age from the year 1950 to the year 2024. Most years from 1950 to 2024, they've collected the median age at the time of their first marriage. So that we're not talking about second and third marriages here. We're talking about the median age men are at their first marriage, and the median age women are at their first marriage. See, it's interesting that they are slightly different numbers. But this comes from the US Census Bureau, if you want to look that up. There are a couple of years, like 2011, where they measured it twice. This was 2 times during the same year, but most other years have just one measurement on it. If you graph that out, where the X value is years since 1950, and the Y value is age, you get for the men's this pattern in blue. And for the women's, you get this pattern in red. So they're just slightly different. Men is just a little bit higher than women, but we can come up with a model for both the men's median age at the time of their first marriage and women's median age at the time of the first marriage. So this data essentially collects, this data set is a collection where the US Census Bureau sees how old people are when they get married, and then they throw out all the non-first marriages, and that's where we get this data. So it turns out if you build an exponential model for each, you can put this trend equation or trend line, it's not a straight line, but you can put a trend line on the graph, and you can build a model for men and a model for women. And this is what you get. The men's median age at the time of the first marriage is given by this. Y equals 21.573 times e to the 0.0044x with an r squared value of 0.9707. The women's median age at the time of their first marriage is y equals 19.069 times e to the 0.0052x with an r squared of 0.9779. And here y, again, is the age at the time of first marriage. Y is going to be the age. X is going to be the years since 1950. So questions like this can be answered. Do these models fit the data well? What do these models predict the median marriage ages for men and women to be in the year 2020? And what do these models predict the median ages for marriage for men and women to be in the year 2080? Let's go ahead and answer those questions. If you want to try these on your own, you can pause the video and try these on your own. In a couple seconds, I will show you how these are done. All right, so men's median age of marriage is given by this formula with an r squared of 0.9707. Now that 0.9707 is well above 0.5, so that is a good fit. Also, the 0.9779 for the women's median age at first marriage is also a good fit. So when it asks, do these models fit the data well? Both of them are yes. Yes, these models fit the data well. And then we'll move on and say, let's predict the median ages for marriage in 2020 based on the equation. Well, for men, it's this equation. Remember, X is years since 1950. So in this case, X is going to be 70 since 2020 is 70 years beyond 1950. So the men's is going to be calculated that way. Median age is going to be 21.573 times e to the 0.0044 times 70. And we just type that into our calculator and get the answer, which in this case is about 29.35. For the women's, well, the women's is given by this equation. Let's highlight the entire equation. And so for the women's, we do the exact same thing, but using the other equation. And for the women's age at first marriage, we type in 19.069 times e to the 0.0052 times 70. And that's 27.44. So that's what this model predicts anyway. This model predicts the median age for marriages for men and women in 2020. For men, it predicts the median age for first marriages to be 29.35 years. And for women, it's 27.44 years. We can do the exact same thing for a prediction that's a long ways out. Now, 2020 was a prediction that was actually a data point in our model. If you looked up, this was median ages of first marriages from 1950 to 2024. So you could see how these predictions fit within the model. On the other hand, if we use a year like 2080, well, that's going to be an X value of 130. 2080 from 1950 is 130 years. So for the men, all we would do is replace that X value with 130. We do the same thing for the women. We'd replace the X value years since 1950. We'd put in 130 and we do our predictions based on these numbers. These predictions would come out as 38.22 for men. That's and for women, it would come out as about 37.49. So based on this trend, it would look like in 2080 that men would see their first marriage, the median age of first marriage, at 38.22 years old, and women would see the median age of first marriage to be about 37.49. Now, this brings up an interesting point about doing predictions with these models. 2080 is a long way away. 130 years since the 1950 mark, but also like 60 years beyond what we're at, almost 60 years beyond what we're currently at now. And this trend, while it looks like we're fitting these models pretty well right now, by the time 2080 hits, this model may be no good anymore. So the question is, would this same trend keep up? Would we still be growing well off into the future? Or would this kind of level out and level off? So it looks like the first marriages, people are getting older and older and older as I, let me rephrase that. People are getting married at older ages, but this trend may level off at some point. It may even go back down at some point. So that's the idea. And that's one thing about predicting way beyond what our model has data for. We have data values between, roughly 1950 and 2024. But we don't know if this trend will keep up beyond that 2024, or we don't know if before 1950 this trend were to extend out to the left. So be careful about predicting outside of known bounds. Sometimes you get some really weird answers, and you can imagine that if you did 230 years out, what you'd end up with. So if you did 2180, that's 230 years. This would predict men to be like at median age of 63 to get married. And women to be median age of 63 as they get married for the first time. That's probably not going to happen. Let's do another example. In this example, we're looking at the number of abortions that take place in the US per year. Now, I know that's always a controversial topic, but because we're looking at the statistics, we're not going to be dealing with any of the ethical pros or cons of abortion or not abortion, whether it's you're pro-life or pro-choice or whatever. We're just going to look at some data here. Again, this is coming from the Michigan Health Statistics. We're looking at X being the years since 2009. So 0 is 2009, 1 is 2010, and so on and so forth. And then the number of abortions in the United States in thousands. So this is like 789,000 abortions, and this would be 620,000 abortions. If you graphed that out, you would get dots roughly going down. And we can fit an exponential model to that data, to those data. That exponential model would come up as y equals 771.85 times e to the negative 0.029x. And the r squared would be 0.9402. So that's what we get through technology. We get this exponential equation. Y is number of abortions in thousands. X is years since 2009. And we also get this correlation coefficient value, R squared value of 0.9402. Let's answer a couple of questions. Let's ask, does this model fit the data well? That's a singular model in this case. And then what does this model predict the number of abortions to be in 2020? According to this model, when will abortions be under 500,000? Again, per year. We'll round all those numbers to a couple of decimal places. If you want to go ahead and push pause on the video and try to figure out these things on your own using this exponential equation that we found via technology and this R squared that comes with it. In a couple of seconds, I'll show you how it's done. Based on what we're given here via technology, again, I am going to be giving this equation to you and the R squared value for any problems in this class. There'll be a companion video that shows you how to do this on your own if you're interested. You can do that in Excel or with a TI-84 calculator. So does this model fit the data well? The answer is yes, because the R squared value is above 0.5. Again, for this class, it's always 0.5 as the cutoff of the R squared. What does this model predict the number of abortions to be in 2020? Remember, 2009 is an X value of 0. So 2020 is an X value of 11. I know I wrote that. So anyways, we take this model that the technology gives and we plug in an X value of 11 and figure out what the prediction would be. 771.85 times e to the power negative 0.029 times 11. That's about 561.04. And that is thousands of abortions that take place in the United States. So that's what the prediction would be for number of abortions in 2020. According to this model, when will the abortions be under 500,000? Well, 500,000 would be a Y value of 500. So all we have to do is solve this equation for X. And the nice thing is we can just use our standard tools. We would take and divide both sides by, 771.85. So you'd get 500 divided by 771.85 is equal to e to the power negative 0.029 multiplied times x. And then I'd take a natural log of both sides. If I take a natural log of the left-hand side, I won't give the number right now, but the calculator can give it to me. 500 divided by 771.85, and then the natural log of that number. That's what's going to be on the left. And on the right, natural log of e to a power is just that power. And then I let the calculator do the work. I take natural log of 500 divided by 771.85. and then I'll divide both sides by a negative 0.029. When I do that, I get an x value of 14.97. Now remember, x is years since 2009. So if you calculate that, if you take 2009 plus 14.97, that means we're talking about essentially the year 2023.97. So almost 2024 would be the prediction there. Now, is this a correct prediction? You could look that up. Don't think it's a perfect prediction by any means, but that's what the model would predict. It would be about 2024 until the number of abortions become under 50,000, or not 50,000, 500,000, excuse me. So there you go. We can utilize, again, just some collected data that Michigan Health Department collects and answer questions like these. Here's another example with some data. This is the number of McDonald's per million people in various countries, along with their Cantrell ladder score, which in general is a measurement of happiness. So it's sort of the number of McDonald's per million people compared to that country's overall level of happiness. And you can see where I got those data. So we have a bunch of countries. I'll use the X value as the number of McDonald's per million people and the overall happiness level judged by the Cantrell ladder score as the Y value. If I put this into technology and graph the dots, you'd get all these dots here. Not a strong pattern for the dots. If I asked to give the exponential regression model, the model of best fit on exponential regressions, it would tell me that y is equal to 6.6208 times e to the 0.0017x with an r squared value of 0.0457. That r squared of 0.0457 tells me that this model does not fit our data well. That r squared is well under 0.5, and so the model does not fit the data well. Now, you could still do predictions, and you could still solve for x with this model if you were given a problem that asks you to do that. We're not going to do that just for the sake of time here. We've already done a bunch of predictions and now solved for x in the previous problems. So we'll skip over that and we'll just say, yeah, r squared of 0.0457 is not a good fit, and therefore this model does not fit the data well. Exponential regression models are not the only models that we can have. We can also use logarithmic models in regression. Now, again, you can go through a huge long process of generating out a logarithmic model by hand that best fits the data. But generally, people just turn to technology to find that. And the models are going to come looking like y equals a times natural log of x plus b, or you can rewrite that in some other ways. Generally, that's what it looks like, though. A times natural log of x plus b. So let's look at some data from 1980 to 2002. And here we have the number of total marriages. This is U.S. Census Bureau data. And then number of interracial marriages. This is in thousands, by the way. So this is not just 651. This is 651,000. So we're talking about in thousands here. So if you look at the number of marriages in 1990, there's 53,256,000. So that's 53 million. And then 964 million interracial marriages. So the trend for interracial marriages has obviously gone up from 1980 to 2002. And so it looks like this. Now, it turns out if you let your X value be calendar years, so X of 1980 stands for 1980, then you end up with a model that looks like this. However, if you let your X value be some other numerical value, so for instance, instead of the X value being 1980, you let your X value be years since 1979. So 1980 becomes an X of 1, 1982 becomes an X of 3. I misspoke there. 1980 is 1, 1981 is 2, 1982 is 3, and so on and so forth. It turns out you get a very different model with a very different R squared. And that is because of the initial bend of our logarithms. Logarithms have less slope, less average rate of change as we move towards the right. And that is a weird thing. Now, that only is the case for these logarithm models. The R squared for a linear model that we dealt with and the R squared for exponential models don't change if I differ the starting values of X. So in previous examples, we used to say, well, let's let X of 0 be the year 2009, or X of 0 be the year 1950. That's perfectly fine if you differ your starting place. If 1950 was actually an X of 0, or if somebody else came along and said, I want to call 1950 an X of 50, you'd get the same R squared value if you built a model and they built a model. And all the predictions would be the same. So the models may change a little bit, but if you're building a linear model, the slope would be the same and all the predictions would be the same. And in the exponential model, the growth and decay rate would be the same and all the predictions would be the same. That's not the case in these models. In these logarithmic regression models, that is not the case. But we can still pick a model that best fits. We can still do predictions. We'll still get an R squared and we'll say an R squared above 0.5 gives us a good fit model, and an R squared below 0.5 is not a good fitting model. So in this case, let's just pick one. I'll pick the first logarithmic equation because it has a better R squared value, where Y is going to be the number of interracial marriages in thousands, and X is going to be calendar years. And let's go ahead and answer these same types of questions with that logarithmic model. So we'll ask, does this model fit the data well? What would the model predict the number of interracial marriages to be in 2010? And based on this model, when will the US have 2 million interracial marriages? Push pause on the video if you'd like and answer those questions on your own. In a couple of seconds, I will show you how this is done with this model. So in this case, does the model fit the data well? The answer is yes. R squared is above 0.5, so the model fits the data well. What would the model predict the number of interracial marriages to be in 2010? Well, again, X is calendar years and Y is interracial marriages in thousands. If we're using this model, this logarithmic model, we'd type in the X value of 2010 into the model, since we're using an X value of calendar years. And then I just calculate the Y. So I type that into my calculator. I haven't done that yet, so I'm currently doing that. 92,367 times natural log of 2010 minus 700,576. That gave me a Y value of approximately 1957.24. So note that that means that many thousand interracial marriages. And that would be 1,957,240 interracial marriages. That would be the prediction for 2010. So there you go. Based on this model, when will the US have 2 million interracial marriages? Well, now what we can do is we can take this model and simply put in 2 million for the Y. Now, remember, Y is in thousands, so 2 million would be a Y value of 2,000 when I plug it in to my model. We can figure that out by adding 700,576 to both sides. So we get 702,576 on the left equals 92,367 times the natural log of X. And then divide both sides by 92,367. So 702,576 divided by 92,367 is equal to the natural log of X. And then to figure out what X would be, we would take e to this power. So I'd probably just calculate that in my calculator. That's about 7.61. And then without rounding it, I'd take e to that power. Usually the easiest way is to just hit your answer mode. But I'll write it out. Let me write it out long ways right now. Excuse me. That's e to that power, 702. That's what's going to be your x value. And what that turns out to be, we probably could have guessed it's pretty close to 2010. It's 2010.93. So once we get to 2011, we'll probably have over 2 million interracial marriages. And once, if you're in 2010, probably just under that. So 2010, just under that. But once you get to 2011, then you get over 2 million interracial marriages in the United States. So there you go. That's what this type of data look like. And that's how you could do a logarithmic regression model. Now, in this section, we've seen exponential models and logarithmic models. We've previously seen linear models. There's lots of other models that exist as well. There's quadratic models that you can create. There's cubic models. There's something called logistic models. Those are ones that look like exponential growth, but then level off. And there's lots and lots and lots of other models of best fit we could use. So the question is, how do we know which type of model to pick? Well, the good news is in this class, you'll be given the model. I will tell you which one to use. But in general, if you're out on your own and trying to pick the best model, you should pick the one that looks the best. In other words, that best fits the data visually and that makes sense in context of the problem. That's usually what people do. They say, should I use an exponential or a linear or a quadratic here? They'll look at the data, look at the circumstance, and pick the one that looks best and makes the most sense. Now, there's another way to go about doing that as well, and that's the way you see on the last line is simply pick the one with the highest R squared value. The one that's closest to 1 in the R squared. And if the linear model has a higher R squared than the exponential, you use the linear. If there's a cubic model that has a better R squared than all the other ones, then you use the cubic model. So again, most people just say, look at the scenario, look at what fits the best and makes the most sense. But if you're ever in doubt, you can simply just use the one with the highest R squared value. In this class, we won't be picking between best models. I will give you those models. But again, if you're out on your own trying to do some regression work, then use common sense. And if you're ever in doubt, just use the best R squared. All right. Well, that's the end of this section on exponential and logarithmic models.